Well, in our previous podcast, we looked at first order reactions. Now we're going to look at zero order reactions. And remember, a zero order reaction, rate is equal to K times A to the zero, or then that just means that rate is equal to K. So what we just showed on our previous slide, right, rate is equal to K. And if we integrate that, we are going to get that A is equal to A naught minus KT. And then if we put in everything that we need for our half-life, notice that the half-life is equal to A naught over 2K. So here, the half-life does depend on the initial concentration. It didn't for first order, but for zeroth order, it does depend on that. And notice that they are directly related. So the higher your starting concentration, the lower, shorter your half-life is going to be. All right, and that might be important. So know that those things are related to, dang it, they're directly related. So the higher the concentration, the initial concentration is, the higher our half-life is going to be. Sorry about that. All right, but that might be something that's important. The linear stuff is not quite as important. Some comes up from time to time that we can draw a figure that has a linear relationship between our concentration of A and our time. All right, so in this case, I have an example of a zeroth order reaction. Just notice that we probably haven't seen this much, but I have gold over the top of this arrow. That means that gold is acting as a catalyst. We're going to talk a little bit about catalyst, but not a heck of a lot during this chapter. Catalyst is just something that facilitates a reaction. Reason that's above the arrow there is because it's not used up or consumed during the reaction. It's just there to allow the reaction to go at a little bit of a faster rate than it would without it being present. So our sample problem here says the decomposition of ammonia on tungsten at 1100 degrees Celsius is zero order with a rate constant of 2.5 times 10 to the minus 4th moles per liter times minutes. Note that this tells us that it's zero order. We don't need the problem to say zero order. This could be gone here, and we would know it's zero order from the units of the rate constant. All right, so it tells us here that we want to write the rate expression. All right, well, we're decomposing ammonia. So we have rate is equal to some constant times ammonia, that's the reactant, raised to the 0th power. Well, it's first order, so really all first order ones are equal to K. Doesn't matter what follows it. All right, part B, which is showing already, and so we probably could have cheated ahead and looked at it, says calculate the rate when our ammonia concentration is 0.075 molarity. Okay, now notice for a zeroth order, the half-life depends on concentration, but notice that the rate does not factor in to this. So the rate is independent of our ammonia concentration. So the rate is just K, and K was given to us in the problem of 2.5 times 10 to the minus 4th moles over liters times minutes. And so the rate is going to be that value for any concentration of ammonia. Well, this slide is just showing the rate expression, the concentration time relation. So the concentration time relation is the integrated rate law and the half-life for 0, first, and second orders. What I'm going to tell you is like this information will be given on exams. So these are not things that we're going to have to memorize, but what you are going to have to memorize is determining what the order of the reaction is so that you use the proper equations. Now we're still in the middle of talking about zero order, and we have one more sample problem to do, and then we'll talk about second. We haven't even brought those up yet, but notice that they have their own set of equations as well. All right, our last sample problem of this podcast says that the decomposition of A is zero order. It takes 35 minutes to decompose 37% of initial mass of 282 milligrams. All right, so there's going to be a little trick in here that you're going to have to follow along with, but part A should be pretty straightforward. It asks us, what is K? What is our rate constant? Notice that none of these equations have any temperatures in them whatsoever yet. And so at this point, we're not that interested in the temperatures, right? There's nothing in our equations that we need that for. All right, but we are going to have to calculate what the K is. So we can say, okay, let's use our zeroth order integrated rate law, which says that A naught minus A is equal to KT. So, this is not that straightforward. Here is where we're going to have to do this. So our initial mass, all right, so again, right, yeah, we want these in moles per liters and stuff like that, but it's good that as long as everything is the same units, we can pretty much use any units we want. So we can use mass here. I don't have to do anything to that. So let's just start with our 282 milligrams. All right, that's our A naught minus our A. So that is how much we have at time t. Well, we decomposed 37%. And so the amount that is remaining, amount left, is 63%. So our A has to be 282 times 0.63, not times 0.37. That's how much is gone. We need how much is still remaining. So 282 milligrams times our 0.63. All right, that's equal to K times our T, which was 35 minutes. And if we work through and solve for this, we're going to see that our K is 2.97. And this is going to have units of milligrams per minute. All right, part B says, what is the half-life of this? All right, well, now we're just going to use our half-life equation there, which is that our half-life is equal to our initial concentration divided by 2K. Well, good deal. We know all that information already. We don't have to look for anything new. Our half-life is going to be our 282 milligrams divided by 2 times the K that we just found, 2.97 milligrams per minute. Look at that. And we're going to end up with our half-life is 47.5 minutes. All right, so again, right, as long as we can find whether we have a first order, zeroth order, or once we get to our next podcast, second order problem, we just need to use the right equations to solve for the information that they're asking for.